Okay. What I would like to talk about today is I'd like to talk a little bit about clustering, and I would like to talk about, which is an important thing, and then I'd like to give back the project proposal, progress reports, and talk a little bit about that. That's my goals for today. Any questions? Okay, so when we talk about clustering, what I guess the first division that I'd like to say is that there is a difference between what we would call supervised learning and unsupervised learning. And supervised learning is kind of a case where you are given you have a bunch of records, each has a feature, each has a target variable that you care about, and you're training on this to try to build a model to predict that target variable. The supervision is the guy that gave you that target variable. That's the way I think about it, okay? And unsupervised learning is basically something you just as input take data, okay, and your goal is to find some kind of structures for it, inherent in the data, okay? Something like page rank, you might argue, is an unsupervised learning method. The input was a network and the output was ranking scores, and it didn't, no one was telling you what the right ranking scores were, right? Similarly, clustering is one where instead of taking data where we have, in some sense, class labels provided for each record, we are in some sense trying to figure out what items are in the same class, okay, and and giving them a label as being belonging to a cluster. Any questions about that? Yeah. Clustering, I would say, is unsupervised. You take any data set, you can cluster it, okay? Supervised means that they tell you what the answers are, and you're trying to build a system to predict the answers on new records, right? There is, for the record, just for completeness, something between supervised and unsupervised learning called semi-supervised learning, okay? Where you take small amounts of honest labeled data from people and then try to amplify it, okay, into bigger collections for training. So for an example of this might be that suppose, let's say, that you have 1 million, input points, and you have somebody label 100 of them as to what class they really are. They work hard on it, and let's say, you have 100 that are labeled as men and 100 that are labeled as women. One way that you might be able to take your unlabeled data set, maybe perhaps you might cluster all the points as an unsupervised way. And then once you've got clusters, you assign all the elements in the input cluster the same label as, let's say we really wanted a lot of data labeled to train on, but it's expensive, let's say, to assign a right label to something. Like, let's say some of you guys work on sentiment, or some people know about sentiment recognition, right? You'd like to be able to read a paragraph and decide if it's saying good things or bad things. Deciding whether something says good or bad things requires a person to read it, and requiring a person to read it costs money, right? You might imagine that if you've got millions of tweets of this type, perhaps instead of paying someone to read 1 million tweets, perhaps what you might do is pay them to read a small number of tweets, okay? Then do some kind of unsupervised clustering of the tweets, okay? And if you find now that there are 2 clusters, these tweets and those tweets, maybe you might now label all the unlabeled tweets in here with the same label as the majority of what you've seen, right? And now you've got 1 million positive examples, okay? And here you've got 1 million negative examples, okay? And you now have the potential to try some method that learns on large amounts of data, where you only paid people a small amount of money to do the annotation. Any questions about that idea? That's what we mean by semi-supervised learning. Obviously, it's better if you could get a real person to read each one of these. They'd be more accurate than the labels we just gave. But failing that, you now have, a large data set, and maybe learning on this large data set might be better than learning on the 100 tweets that you were able to just learn, manually classify by themselves. Yeah?
So your training data does not really have labels attached to it?
So in an unsupervised problem, your training data does not have labels.
So that's why you cluster them and then you provide
Clustering is a good way to provide labels, because if you have two clusters, if this is cluster 1 and cluster 2, everything in this cluster you can say has label 1, and everything in this cluster has label 2. Okay? So clustering is a way to provide labels to things that aren't otherwise labeled. Okay? And as we were talking about under a semi-supervised method, sometimes perhaps if you have a small number of things labeled, you can leverage the clusters that you found and use that to kind of give you the effect of having labeled a lot more with the labels that you want them to have. Any questions about that? Okay, but that's not what I really want to talk about. I want to talk about clustering. Okay? And clustering is the problem of grouping points by similarity. And the reason why clustering is a important problem is that often in our data there are usually a small number of classes or sources or explanations of the things that our data comes from. And clustering, because it groups things that are similar in the same cluster, it's often a good way of revealing how many explanations or sources or something there are. And the key idea here is that we're going to be interested in, given points, how similar are they? Similarity of points gets back to our notion of distance functions. Okay, so we talked, I believe it was last class or the class before, about distance metrics. We're going to use that basically to underlie our clustering. Any questions? So clustering is an important problem, but it is a somewhat ill-defined problem. Okay? If we take a look at this data set here, okay, I want everybody to think how many clusters they see in this data set. Okay, here's some data. Okay, how many people see one cluster? This entire thing. This entire thing is the data set. Okay, how many people see one cluster? 2 clusters. 3 clusters. See a bunch of people. How many people see 4 clusters? A couple more. How many people see 5 clusters? How many people see 6 clusters? 7 clusters? 8 clusters? 9 clusters? Okay? So some people see 3, some people see 9, a couple of weirdos saw 4. Okay? Who's right or wrong? Okay? The answer is nobody is right or wrong. Does everybody kind of see that clustering is a somewhat subjective problem? Okay? And I mean, you can define a metric of what you're trying to optimize on your cluster. Like, let's say, minimize the sum of the distances of points within a cluster divided by some. So you can certainly define an optimization criteria. But that's a little bit different than saying, how many clusters are really there. Okay? So typically when people think of clusters, they often think of kind of the Platonic ideal, or these kind of circular compact clusters. But sometimes you get clusters that are long, straight things. Sometimes you get nested clusters, right? And, depending upon what your application is, you may want to see 3 clusters here, you may want to see 9 clusters here. Conceivably, you may want to see something in between. Yeah?
Wouldn't a point on the line be closer to the bottom point than it would be the end point on the line?
Which one would you say?
So like the bottom example, top line, right? Wouldn't like a point there be closer to the point beneath it than it is to the point all the way at the end of its own?
So you're saying one problem with skinny clusters is this point is closer to this than it is to this one, right? So the question is, do you see, why is it that this point should be in the same cluster with that instead of this? And to a certain extent, that is a function of your, your criteria of what you're hoping to see. I guess the philosophy would be that there's, if you're assuming you're sampling points at random, the presumption is that there's relatively few points in between these two clusters. Does everybody kind of see that? So the argument for why this and this is in the same cluster has to do with the intermediate points. Now, is that right, or should we be looking for circular clusters or not? The people who said there were 3 clusters in here said they were looking for circular clusters, right? And the people who said there were 9 clusters said, yeah, these are clusters as well. Okay? And I will claim that it's somewhat application specific what you want the answer to be. Any question? One thing in general, there's a lot of people, we will talk about a couple of classes of clustering algorithms. It is universal that people run clustering algorithms and are never happy with what they get from them. Okay? They always think there is something wrong with their clustering algorithm. And the reason, I think, is partially because they have what their internal criteria of what they're trying to pick up on is often a ill-defined thing. Okay? So there's no shortage of clustering algorithms on the world. We're going to talk about 2 and maybe 3, although I think we're going to talk about 2. But two types of clustering algorithms. But in general, you have to think about what you're actually hoping to see here. Any questions? Here's another clustering example. This is a real clustering example from some biologists that I work with. It's kind of a famous experiment in biology. This has to do with trying to figure out how the cell cycle in genes work. Okay, and what do we read this picture as being? Each column here represents a gene. Okay, this is in yeast. Each column is a gene in yeast. Each row here is a measurement of how turned on that gene is as a function of time. Does everybody kind of get that idea? So you can imagine they're looking at these genes for over time, and this gene looks like it's off, and then suddenly it goes on and it goes off again, right? This is one that was not on very much, but it kind of becomes negatively on. It goes down even more then. Okay? So if you look at this thing, we've got genes on the x-axis is genes, the y-axis are different measurements of it. What is this thing looking like? Okay, this represents a clustering of the genes, okay, so that similar genes are, in some sense appear next to each other. Does everybody kind of get that idea? In fact, there's kind of a tree above here. The important thing to see is that tree here. This is describing kind of a merging tree. And if we look at how we're interpreting it, all the stuff on the left of the merge, which in this case looks like it's up to here, is more similar among itself than all the stuff to the right of that merge. Does everybody kind of see that? And that the way to read this is this tree is kind of, again, if you look at it in this side, these bunch of genes look similar. These bunch of genes look similar, and these bunch of genes look similar, right? This is kind of showing pairwise merges. The higher the merge is getting, the less similar the merge of the clusters are. But basically, this is building clusters by merging smaller clusters together. Each gene was originally in its own cluster. Any questions about that? And so what does this show? This shows that all the genes, as you run through the cell cycle, seem to fall naturally into a relatively small number of classes. You guys are not biologists in here, but if you say how many different types of genes are there, well, you'd probably say, well, gee, there's one type there, there's another type here, there's another type here, there's maybe 2 little subtypes over there, this type looks different, these are a bunch of weirdos, they don't look quite like anybody, these guys are all the same and those guys are all the same. Does everybody see that? So from going from an undifferentiated mass of genes, suddenly you've got natural clusters that emerge. They're being turned on and turned off at the same time. And now the biologist would want to ask, why is that? Okay? And it's clear that you're in much better shape than if you didn't have this clustering. Any questions about what it was doing or how you read this thing? And for the record, how many points dimensions is this data that we're clustering? We're clustering, it looks like here, a few hundred genes. In fact, in the full paper, it was clustering something like 6,000 genes. And you have something like about 10 different time points or something like that, 10, 15 time points. So this is a clustering of, 10 or 15 dimensional data, okay? But it's in a way that now we can see what's going on and it makes sense. Any questions about that? Yeah.
So x-axis is the increasing distance.
X-axis is the genes, and they've been permuted to show off the tree, okay? So does everybody get the idea that this is a listing of genes? These genes are not appearing in alphabetical order. Does everybody kind of get each gene has a name, but they're not appearing in alphabetical order? What had happened was there was a merging, and this merging created a tree. And this is saying at the highest level merge, the root node, put all the genes on one side of the merge to the left of all the genes that are on the right side of the merge. Does everybody see that? And it recursively does that kind of thing, okay? And it comes up with this kind of drawing. Any questions? Okay, good. So why do we cluster data? Clustering is a sort of zeroth order thing to do. It's, if you're given a data set, clustering it is one of the things you're supposed to do with it. Why do you do it? Well, one is what I would say is hypothesis development. Figuring out how many distinct populations there are in your data. When they first did these experiments on genes, they had no idea how many different types of genes were involved in the cell cycle. After you cluster it and see how many natural clusters there are, suddenly you've got an idea, right? Any questions? One reason why you do clustering is that you might want to build a separate model. If you have a large universe of things, you might want to, instead of to build a model for smaller numbers of things. So let's think about it. Let's think back to the let's say the baby weight project. Okay, if I think of the baby weight project, there you had a group that had 150,000 babies, okay, or parents in baby situations, and they could build a regression model over 100. If you think about it, they had something like, if I remember, 150,000 babies. They had something like 50 features on each baby or mother or something like that. And you could try to build a regression with 50 variables to try to predict the weight. Does everybody agree with that? But are there different populations of babies that we would kind of imagine? Okay? I mean, I kind of imagine that there are, there are classes of low birth weight babies, right? There are classes of different things. There's what happens with twins. Are twins a special class of babies? The answer is yes. Okay? Do we expect that the weight of twins to be different than the weight of regular babies? Presumably. Okay? We could try to have these all as models that were built in. Okay? We could have one model and try to predict it for all cases. The other is to take those babies and cluster them into a small number of natural classes. Okay? Suppose I clustered it into 30 types of babies. Now I've got 30 babies, each of which have, 5,000 test cases. Does everybody see that? And now my model might be build a separate regression for every one of the clusters. And when a new baby came along, what could I do? Figure out which cluster does it look like it belongs, and then use the weight formula for that baby. Does that kind of make sense? So you can imagine that a lot of the world, certainly the Googles and the advertising agencies and all these kind of things, they cluster people Okay, and then they build models over like groups of people. Okay, so that it's better than building one generic model on the whole thing. Any questions about that? So that's a natural reason to go and do clustering. Yeah.
So that 5,000 size of a cluster.
Yeah.
Should that be like this? There should be some threshold after which we should say that we can build one cluster out of these many number of.
Okay, so what is clear is, so you're saying how many clusters should I build here? Well, part of it is, it should be a number of clusters that are naturally reflecting real things about babies. You wouldn't want to artificially split a cluster just because you want to cut it in half. But if there are a certain number of conditions that cause natural breakdowns of the population, then you would want to build a model for each one. And the question of how small should your clusters be? Well, the way I think about it, you've got 50 variables. If you were doing linear regression, you probably need at least 100 training examples or 200 to do something meaningful with the linear regression, right? But again, if the classes are distinct, you're better off building a separate model on them. If the classes are the same, you're doing nothing by kind of drawing lines through them and separating them. Any questions? Another thing to do is data reduction. Suppose I give you huge numbers of points. Okay? Sometimes quite often, you are given millions of points of input, but many of them are essentially the same thing. Okay? If you had a data set where you had billions of things like this, and that they were, let's say, 1,000 real clusters, each of which cluster was very, very tight, you're probably not going to learn very much training on those million instances. Much better would be to pick the center of each cluster, maybe have only one representative from each cluster. And now you've got 1,000 training points that really have differences, rather than a lot of training points, all of which are the same. Any questions about that? Okay, yeah.
So it doesn't necessarily apply in the face of the modeling over smaller groups, or are those contradictory things?
Well, it depends. So the question is, if you have essentially there's a question of whether a small group is, views of the same thing, or if it's a different condition, right? It could be that, let's just, again, with all of these things, there's some engineering decisions to be made, right? But it should be clear that if you have duplicates of the same point, you want to remove duplicates. Okay, that's often a thing you'd want to do, right? Might you want to remove near duplicates? If it's, let's say, a measuring error or something like that, quite likely you might want to do that, right? So I will claim that for identifying how many real different types of elements there are, it sort of is a clustering problem. And I guess, yeah.
So if it won't clustering, I guess what I'm saying is, won't clustering give us, in this case, clustering is giving us separate populations.
Okay, in the first one, for item number 2, this is saying if we have a certain number of real differentiated populations, we could identify them as separate groups, and then understand the let's say, distribution of what's within a population. In another case, when you've got things that there really isn't a very interesting distribution within the population, but they are drawn from many different populations, then perhaps replacing the item by its centroid is a good thing. Okay? So again, these are somewhat fuzzy things, but sometimes you want to build many models, and sometimes you want a simpler model on a small number of items.
But clustering does give us separate populations. I mean, is that one way to
Clustering should be finding separate populations. That's kind of what it should be doing. Okay, yeah.
These smaller groups that you're eventually going to find, it depends upon the number of features you use, right? I mean, won't that change if I take a smaller number of features and I get different number of clusters?
So you're right in saying that if you use, if you have features that are completely independent of each other, You know, let's say everybody was made up of features of half human and half fish, okay? Then if we cluster according to the fish features, we might look different than if we were clustered according to the human features, okay? Ideally, when you're clustering, you probably want to take all of the representative features.
But even if I do remove correlated features from the model, and I say end up with out of 50, I end up with say 10.
Yeah.
Absolutely independent of each other. From that 10, depending upon what I take, will determine the number of smaller groups, right? And that may change.
Okay, in general, when we're clustering, I'm assuming you're using all relevant features to cluster.
Yes,
Okay.
but if you're using all of them, even if I'm using all those relevant clusters, all those relevant features, I will end up with different populations every time if I take some and do not take the others, which may or may not be relevant, right? Relevance will depend upon my problem statement, doesn't it? What I'm asking is, I will end up with different populations depending upon the features I take, right?
Yeah, certainly, if you use different features, you would end up with different clusters, okay? That's why generally you would be building it on all the features that you would have that you feel interesting. That's kind of, what it is. A final application for this would be outlier detection. Often you're trying to figure out which items don't really belong with other ones. These would be arguably either they're going to get stuck in a tiny cluster by themselves of weirdos, or perhaps they're going to be the items far from the cluster centers after you cluster them. Any questions? So we stick it in this cluster, this big cluster, but it's really out there, and so that's probably a sign that it's an outlier. Any questions? Okay, so that's why we would care about clustering. Okay, how can we find clusterings? I'm going to argue that there are, I'll talk about at least two different kinds of algorithms that I think are interesting. The first, that is probably the generic computer science algorithm for clustering, is something called k-means clustering. What the basic idea is, you start with you have endpoints. If you know you want k clusters at the end, you pick k points randomly as the center of clusters, and then go through rounds where what you're going to do is to assign all the examples, okay, to the center that is nearest to it, okay? And now points are now associated with centers. If you have all the points associated with a particular cluster center, now if we take the centroid of these points, we would compute a new center. And kind of what k-means is doing is iterating through and starting from random guesses as to what the centroids might be, the cluster centers might be, okay, assigns points to the nearest one of these centers. Now that you have a bunch of points grouped to it, you can now recompute the centroid of each group, and the hope is that it's going to kind of hone in on what are the real cluster centers. You started out with essentially random choices for the centers, and the hope is that you're going to move these things around until you find the right centers. Any questions about that? So here is an example of what happens on a similar kind of example to what we showed when I give you 3 centers and I run k-means on it. So what is this first example? I picked 3 points. Here we kind of agreed that there are 3 centers, and there are really 3 clusters in this thing by at least some definition. Let's pick 3 points at random. If we pick 3 centers at random, we pick this, this, and this. Does everybody see that? Now you may say, wait, but I wanted one in there. Well, you don't know that. You picked it at random, right? Now, when you do that, the next step is going to be, how do we refine our choices? We will assign every point to the cluster center which is closest to it. Does everybody kind of see that's what we did with these colors? Certainly for the 2 cluster centers down here, if we define the perpendicular bisector between those points, that kind of describes the partition of which points are nearer to one center than the other. Does everybody see that? So the perpendicular bisector here kind of cuts this thing into 2 pieces. Does everybody see that? The other center up here and here, what would the perpendicular bisector of that look like? It looks like it's something like this. And the net result is that this bit when we assigned points to which center was closest, these were closer to this point than it was to that point. Okay, otherwise we got for purple this mix of the top part of this and all of that. Any questions about that? Now, once we've done that assignment, what is going to happen to the centroids? Let's think about it. Where is the centroid of the red point? This is the centroid that defined the red points, right? But now, where is that centroid going to go? Okay? It should go to the upper right because it's going to be picking up these points. Does everybody kind of see it? So the centroid shifts up there. What about these guys? There's more points down there. It shifts down there. And what about this one? There seem to be enough points here that the centroid shifted out there. Does everybody kind of get that? And now again, we reclassify points as to where are they closest. And in this case now, the good thing is this stopped being split. Now blue picked up all of, this cluster picked up those two bars. The red cluster picked up this and this, and the purple cluster is up here. Any questions? When we drop this thing, now the red points move down. The purple cluster, I gather, moved up a little bit. Okay? This cluster was basically where it was before. It didn't really change. Okay? And you keep going through these iterations until it stops. Okay? Why would this stop? It will stop if when you think about what the process is. We take the current points, we find the centroid, we assign points now to their nearest centroid, right? If the partition of the points into groups doesn't change, it's never going to change again. Does everybody kind of see that? And so eventually it'll stabilize, and in this case it happened to have stabilized on the right answer, okay? It took its while to getting there. Actually, this is what we designed those points so that it took quite a while. It took several iterations until it could kind of push more and more of this red stuff out, okay? And once it had finally pushed the red stuff all the way out, then now when it took the centroid, it found the center as being in the middle of the red ones. Any questions about how that works? Yeah. Can it never be ever be unstable? So what does unstable mean? Okay? Unstable should mean, okay, you say things flipping back and forth, back and forth. It shouldn't be unstable. Okay? Way that I should think about what's the worst thing that can happen. Let's say you have two classes. How many different potential subsets of points are there until that we might get each one of these iterations is in some sense defined by a subset of points. If you got extremely unlucky, conceivably it might iterate through all 2 to the n subsets before it finally decided it had settled down. Okay? So I won't say it's not unstable in that you can't get into an infinite loop, but it is potentially going to take you a long time to get to where you converge. And there is no reason why when you converge, you actually converged on the right point, okay, on the right points. It's quite possible you could converge on a local optima here that is not a global optimum. Is that clear? Yeah.
How did we know to start with 3 points?
Okay, so there's a couple of different issues with k-means clustering. The first question is, how do you know what value of k there is? And we'll talk about that in a second. Okay? Another issue would be that, again, you know, in a world where these are going to converge on a local optimum, okay, there's a question of maybe you want to try this a bunch of times and take the best possible solution that you find, okay? Any questions about that? What is the running time of this algorithm? Let's think about it. If I have n points, k clusters, and these endpoints are in d dimensions, how long should k-means take? Okay? Let's think about that for a second. Or how much is one iteration of these k-means going to take? Okay? So there's the first part is I give you cluster centers, and I've got to decide which points closest to for every point, which cluster center is it defined by, right? So what is that going to do? That's going to be basically something like you're going to sweep through all endpoints and compare them against all k-centroids. Does everybody agree? So to compare a point against a centroid takes how long? D. So it's something like NKD per iteration. Does everybody see that? Now, how many iterations should it be till it converges? Well, hopefully relatively few, right? And of course, you have it in control. If you feel it's making small enough improvement that you want to stop, there's no reason why you can't stop. Is that clear? So you would multiply this by the number of iterations, which would be I. Does everybody kind of get that? And I will say typically I is 10-ish or something like that for a reasonable point set. Okay? And you may want to try this with multiple sets of restarting. So let's say R is going to be the number of restarts. How many sets of random points do you want to try at the beginning? Then how many iterations do you want to run of time proportional to this? And then take what is the best clustering of the bunch. How would you measure how good a clustering is? Suppose I have a bunch of points here, and I have my centroids. How do you measure how good that clustering is? Okay, so one part, you're saying draw the smallest circle around the points. That's what I think you're saying, right? That would figure out what's the worst point. The circle here would be defined by what is the worst point in each cluster. Does everybody see it? Perhaps we could sum the ratios of that the radii if we wanted. I would probably be more inclined to take like root mean squared error, right? Where I sum up for every point what's the distance between it and its center, and take the square root of that. Okay? Any questions about that? So one way or another, this gives you a way to find a clustering, and it gives you a way to we now have a way to measure how good it is. So if we took multiple restarts, we would know which of the set of cluster centers is the best one. Any questions? Okay, good. So what other issues do we have with k-means clustering? One issue that's interesting is what if our feature vector has things that are not numerical points? Okay? Let's say with the baby weight or with some other kind of a data set. You could imagine you've got height, weight, gender, citizenship, stuff like this. And under gender, you might have female, female, male, right? If you have a height, 68, a weight, 135, what is the problem if we have a mix of numerical features and categorical features? It's a distance function. Well, a distance function is not necessarily such a thing. You could define a distance function between what the distance is between an M and an F, right? Perhaps the distance between two things of the same label would be 0, a distance of 1 between things across genders, right? So it's not a problem. There's no real reason why you couldn't define a distance function on this. But what is a function in the context of k-means? Okay? We are trying ultimately, remember, to represent the cluster by its centroid. Does everybody kind of see it? How do you compute the centroid? Let's say this was 72, this was 74, 5, 140, 137. How do we compute the centroid of these points, right? This is a point in 3 dimensions. Does everybody kind of get it? The centroid is really, we sum up and compute the average value in this coordinate, right? The average value in this coordinate, right? The average value in this coordinate. What is the average value of this coordinate? What's the average of 2f's and 1m? Okay? It's in a categorical world, you can't interpolate between values. One of the nice things about numbers is there's always space between them, right? But in categorical situation, you don't have that. Does everybody kind of see that? So how can we deal with the, can we use k-means for categorical data? One idea is that we could, if we had a bunch of points here, instead of computing the centroid of it, we could figure out which was the centermost point among the examples. Does everybody agree that even with these fields here, we could still compute a distance between points, right? So what would the center be? The center would be the one, perhaps, that minimizes the maximum distance to any of the other points in the center. Does everybody kind of see that? So we could use one of the points itself as a representative of the cluster. Does everybody kind of get that idea? The centroid is making up a new point to represent the cluster. A so-called meteoid or something like that would be picking one of the inputs as the representative of that cluster. Okay? Okay?
So I understand that we have a hard time with.
Okay, suppose these were my points. Okay? Does everybody kind of see that if I want to, what k-means needs is a representative center of each cluster. That is what the algorithm is doing, right? It is defining clusters by a center thing, okay? And what we're saying is, historically we defined the center as the centroid of numerical values. But another possibility is we take one of the real points as being the center, okay? And picking then the point that is kind of in the center of the resulting cluster. Here we could still use labels on that point, right? There's no reason why this point has to be defined purely in numeric space, okay? And it still captures the idea of being a center representative of the cluster. Any questions about that? Okay? Yeah.
So in this, you already have a cluster at this point, right? When you're finding the distance or trying to minimize the distance, like, so it's not like the initial problem where it is not already clustered.
Well, no. Even in the how does k-means work? In the beginning, it isn't clustered, but what does k-means do? It picks k centers, right? In this problem, it would pick k examples at random, right? Now each of you is a center. Let's now go through and assign points to its nearest center. And now we've got a cluster for this thing. Now let's reinterpret that cluster by finding the center of the points that are actually in it now.
So like when we had the centroid, it was just a calculation, right? Like, no, but even then, how do you limit the scope? Like when you have like 3 random points, let's say from a set, at some point you have to like stop calculating, right? That only for this region I want to find the centroid. Like you have to.
Okay, I'm not hearing what your problem is. Say that again.
So let's say there is a set, right? And you have not done like even one clustering iteration till now, and you take 3 random points.
Yeah.
So now when you want to find the centroid from the initial calculations, you need to be able to do some sort of mathematical operation.
Okay, you need to be able to do a distance computation. Once I have a representative or a centroid or a random point, whatever I want to do it, I need to be able to go through all my examples and say, which of these centers is this point closest to? That's just a distance computation, right? So the thing you need to be able to do is a distance computation between examples, right?
So you're taking all the points in that.
I'm going to take all the points and assign them to the closest center that I have, right? Once I've done that, my next phase is to find the centroid, a new centroid for each cluster, okay? which is hopefully closer to the real center of that cluster. And I'm going through these same number of iterations of, once I have new centroids, assign points to the centroids. Now recompute the centroids. If no point has changed its assignment, then I'm done. If not, presumably it has gotten better. Any questions? Yes? What? Well, we could say it's 0 and 1, but in general, if we have hair colors, when there's multiple ones of these, again, whenever we have categorical data, if you want to compute a distance between it, you need to have a problem-specific notion of what is the distance between two of these labels, right? And depending upon what your application is, one possibility is that it's 0 if the two labels are the same, and 1 if it's different. Another is you may have an idea that some of the labels are closer to each other, and that if I misclassify you as an electrical engineer, that is less of a problem than if I misclassify you as a poet, okay? Because computer science and electrical engineering are kind of closer to each other, right? So the point is that for any fixed categorical labels, you have a distance between them. And once you have defined that distance function, you can do a k-means type algorithm on it. Any questions? Okay, good. Now, the big question which about clustering that we had talked about, that we're mentioning, is that there is this question of how many clusters do you have? Okay? And usually, sometimes from your application, you know how many clusters there are. If you're clustering people, you may think you want genders to pop up, and there's, maybe you think there's 2 of them. Okay? But in general, one idea is we define like the mean squared error, or the sum of squared error, okay? And one clue to figuring out how many clusters there are is to build a plot where the x-axis is the number of clusters, and the y-axis is the error we get when we cluster the points into that many number of clusters. Does everybody get an idea what I mean by error? Suppose, let's say I had point set that looked like this. Okay? How many clusters should I use? Well, what if I try 2 clusters? What are my 2 cluster centers going to look like? Maybe it's going to be there and there. Does everybody see that? And if I now, these are all going to get assigned to this, and this is all going to get assigned to this, I can now compute a sum of squared error, right? I measure the distance from here to here, and I can either sum up the errors or sum the squared of the errors, and I get a score. Does everybody see that? Now what happens if instead I go and add 3 cluster centers? Okay? Does everybody see that if I now take a look, all these points are assigned to this center, the sum of squared errors between the point and its, the center and the points in its cluster is going to be much lower. Does everybody kind of see that? So does this tell us why we use 3 clusters? What's going to happen if we use 4 clusters? It will still decrease. This is a problem. What would be if we want to minimize the sum of squared errors for our points, and we didn't care how many clusters we used? What would be the right number of clusters to use? N, everybody be in its own cluster, right? Sum of squared error is now 0. Okay? So the important thing is we do not want to minimize the sum of squared errors. Does everybody kind of get that? The more cluster centers you add, the lower and the closer and closer everybody is going to be to another center, right? Here, if these were McDonald's, these people are all served by 3 McDonald's. If somebody insisted on putting in a 4th McDonald's, right? We could do it, right? And if some people are going to have a shorter trip, right? So what is the idea? Basically, if we plotted the number, the error as a function of k, we would expect that the number of clusters that the error, we're kind of looking for where is there the point where adding another cluster doesn't really decrease the error very much. Does everybody kind of get the idea? So we agree that it should be, our objective function should be some function of the number of clusters and the error. Okay? So we're not fooled to just lower the error arbitrarily. Yeah.
So then if we're calculating the running time of the algorithm, do we do this for k being k equals 1, k equals 2, k equals 3?
So a reasonable thing is to run it again for all the different k's that you care about, right? To get a sense as to how many clusters there are.
But then do you just look at a plot and be like 3, or do you
So, this now then gets to be an art. One, in general, I would look at the plot and say, yeah, that probably looks like it's a 3. Okay? There are more formal methods that are used to try to optimize this. So if you take a look, I don't think I have a slide that says this kind of thing. But basically, if you, there are different criteria that try to balance the number of parameters and the error. So if you learn about like the AIC or the BIC, these are kind of methods that try to compute a score to combine them. But to my mind, to a certain extent, it's often an eyeballing thing. Any questions? Okay. Fair enough. Again, this case, I took our data set and I clustered it with k equals from 1 to 9 clusters. Okay? And so if we look at what k-means did on it, I find it kind of instructive. For one cluster, everybody's in the same cluster, right? For 2 clusters, you got 2 pieces and it divided it this way. 3 clusters, it looked like it did the right thing. 4 clusters, it divided these things up. 5 clusters, it split that off. Okay, although in this case, for some reason, instead of these 2 being together, it decided that those 2 were together, right? 6 clusters, now these 3 are separate. These things have been partitioned. 7 clusters, these have formed 3, but look, these 2 got split, right? Again, if we ran it another time, perhaps these 2 would be separate. Okay, this is an example of the fact that when you run it once, you don't necessarily get the global minimum. Is that right? Here, when we ran it on this example for up to 9 clusters, it did everything right except for the circle nested clusters. Okay? Generally speaking, k-means is going to have trouble with nested clusters because there's no way to put the center of these 2 clusters are exactly the same place. Does everybody see that? And they generally would have trouble with long, skinny clusters. Okay? Any questions about that? Okay, but k-means is a good thing in general. Okay, any questions? And the other class of clustering algorithms, that is what we kind of talked about, the main class, is something that what you call the agglomerative clustering, where if you think about k-means, it's sort of top-down in some sense. It says, here, I want to say, here are the cluster centers, and then groups them like that. Agglomerative clustering is a bottom-up method, where it says that originally each point is in its own cluster, okay? And what it's going to do is repeatedly merge 2 of the points, the 2 clusters that are nearest to each other. And you can kind of imagine originally you have n separate points. It's going to merge the pair that is closest, merge the pair that is closest, and keep doing it until the entire thing is one cluster. Does everybody kind of get that idea? Now, which algorithm that you have seen is this like in, in your graph algorithms class? Which algorithm is this sound like? Minimum spanning tree. Which minimum spanning tree algorithm? Not Prim's. Kruskal's, well, from your expert thoughts, okay. Yes, so it's like Kruskal's algorithm, right, where originally everybody is in their own component and you merge the 2 closest pairs. Does everybody think about it? So minimum spanning tree is in fact an agglomerative clustering algorithm called single linkage clustering, where we're going to say we're going to merge 2, 2 clusters based on the distance of the nearest points within the cluster, right? If you think, what was Kruskal's algorithm going to do with this example where there were points there, points there, points here? What is Kruskal's algorithm going to do? It'll find the shortest pair to merge, closest pair, 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 closest pair. Does everybody kind of see that? Where are the clusters? When you finish building the minimum spanning tree, how many clusters do you have? One. How do you get multiple clusters? You delete the long edges. Does everybody kind of see it? Or let's say you stop when the merging is too big for you. Any questions about that? So that is the idea of agglomerative clustering. Now, basically, the agglomerative clustering algorithm is going to be n rounds of find the nearest pair of points. Okay, find the nearest set of pair of clusters to merge. Okay? And what nearest means is different when you talk about clusters rather than points. Okay? Here we've got two clusters, the red points and the blue points. Does everybody think about it? What is the distance between these clusters? If we take the nearest point between the two clusters, that's going to, that would be defined by this. That's the minimum spanning tree criteria, correct? What is the shape of clusters we would expect to get if we merge them according to a nearest neighbor kind of thing? Do we think that's going to produce round clusters or not? Let's think about it. Okay? You know, if I say two clusters are, I have a big cluster like this and a big cluster like this, okay, it only takes one edge to decide to merge them. Does everybody kind of see that? So it's not going to work very hard to keep the clusters round, is what I kind of want to say. It is very, very easy if I have a long chain of points like this. What is the cluster going, if I did something like this, and I had this point sitting out here, what are the clusters that you're going to get? It's going to be very, very happy to say that all of these guys belong to one long skinny cluster. Does everybody kind of get that? So if we merge according to the single linkage criteria, it's not going to try to, basically only one pair of votes get one pair of points get a vote. Any questions?
Yeah, how do we, do we put points, how do we determine the clusters to
Well, originally, every point is in its own cluster.
Right,
Then we're going to merge the pair of clusters that are closest to it, that are the nearest pair of clusters, right? So if in the single linkage, it would be the nearest pair of points. So that's what minimum spanning tree is doing, right? It's taking up, finding which pair of points is closest and merging them into a component. Then it's saying which pair of points from separate components is closest, and it merges them, merges them, merges them, right?
Does it just like take an average distance between the two points?
Well, in single linkage thing, what nearest neighbor does, what minimum spanning tree does, the answer is no. It only bases it on the closest pair of points. In some sense, if we did it that way, the merging decision is based on what basically are outliers of each cluster, right? The outer points on each cluster are kind of what's going to be governing them. So nearest neighbor is not a terrible idea, but it's not a very robust idea either. Another idea might be to try to take the average distance between the points. Does everybody kind of have the idea? If I'm trying to decide, should I merge? I have three clusters. Recognize what my problem is. I've got clusters A, B, and C. I want to decide which cluster is closest to each other, right? One possibility was to merge based on the nearest point. Another might be to take all the points in this cluster and compare it to all the points in the other cluster and sum up, find what is the average distance between points in this cluster and points in that cluster. Does everybody kind of get that idea? Therefore, then it's going to merge two clusters if all of the points are relatively close to each other. Does everybody get that idea? So this is probably a more robust decision. What is the problem with that? It is a more expensive calculation. Does everybody kind of see that? If I have x points here and y points here, the distance computation of how far apart are x and y is an order x times y calculation. Does everybody kind of get that? Okay. What is a good compromise? A good compromise is, what if we take the points and find the centroid of each point, of each cluster, and now measure the distance between clusters as the distance between the centroids? If I have x points in this blue cluster, how much time does it take to compute the centroid here? It's order x, maybe x times the number of dimensions, right? So now then, instead of this being x times y, this then would be an x plus y computation, right? Compute the centroid, which would be linear over all clusters, okay? And then just compare the distance of the centroids and merge two centroids if they're closest. Any questions about that? Okay? And there's a final criteria which is sometimes used called furthest linkage, which is link two clusters if the maximum distance between the clusters is minimized. Okay? Why might we want to do that? Okay? So we're trying to decide how similar are these clusters. What if we are taking the furthest points between the two clusters as our measure of similarity? Okay? Well, this is the worst case scenario of the two. Okay? And it's going to try to minimize the worst case scenario. What shape would minimize the worst case scenario for a bunch of points? Something that's very round. Does everybody kind of get that idea? So if you're trying to produce round clusters, this is not a terrible idea. Any questions? Okay? So bottom line, there are these different linkage, when you look at these agglomerative clustering procedures, they are defined by these different linkage, conditions. And again, there are simple ones that tend to be fast to compute, and there's more complicated ones that are more expensive to compute. And what you want to use is, becomes a design decision. Any questions? Okay? And again, there's a cost, basically it's a cost here. So typically with these agglomerative clustering procedures, if you do them, in a simple way, they're basically something like n squared total. And if they do them in a more complicated way, they are n cubed total. Any questions about that? Okay. Now, which is better, agglomerative clustering or k-means clustering? And the answer with all these things is it depends. Okay. But one advantage of an agglomerative procedure is that it does give you a hierarchy of mergers. And these hierarchies are often good things to have. Okay? Why would a hierarchy be good? Well, one, in most problems, the world is not organized that there really are distinct clusters that are really kind of distinct. Typically, there's gradations, there's shades of difference and things like that. And so in an agglomerative procedure, you actually do get to have a natural organization of clusters and subclusters. Okay? And you can actually often view it. Again, when we remember back to our gene situation, we didn't get at the end, there's two different kinds of genes. We got the idea that there are these natural clusters and subclusters, and we learned more about it, and we got a nice visualization of it on the process. Any questions? We also can get other things. One thing that's good about a hierarchy is it gives you an efficient way to classify new items. Suppose, let's say, we had a world like, let's go back to this thing, where we had a large number of different clusters, okay? We had a hierarchy on top of it. Suppose we had a new point came in. There was another gene that someone discovered, let's say, and they had the points associated with it. How would you figure out which cluster it would go in? Okay? In a k-means situation, how much time, if I give you a k-means situation where you've got k cluster centers and I have a new point come in, how much time does it take to classify it? I've got to classify it against all k of my things. Does everybody see that? For small numbers of clusters, that's not bad. For large number of clusters, that is potentially expensive, right? But what does this say? If each one of these clusters was, let's say, defined by a centroid, now what could I do? At the top of my tree, I have to decide, is the center I want on this side or that side? If I compared it to, if I had a centroid of the points on this side and a center of the points on this side, comparing my input to those two centroids, I could decide which one of those was it closest to, right? And so in principle, in time proportional to the height of the tree, I should be able to find what my right cluster center is. Does everybody kind of get that? And so for certain classification things, having the, the hierarchy is a good thing to have. Any questions about that? Okay, yeah.
With k-means, don't you generally have larger clusters? Do you go into a lot, if you have like some kind of data where you're going to have, like you want like a lot of different clusters, would you really use k-means?
Okay, so k-means, remember, we saw the running time was proportional to the number of clusters. The hardness of finding the right thing is going to be proportional, increase. The difficulty of finding the quote-unquote right centers increases as we add more centers. So generally speaking, for k-means, you probably want k to be relatively small.
So in practice, generally for large data, where there's a lot of clusters, you don't really use.
When you have a large number of clusters, I would say it's probably less desirable, okay? And so I think you're right there, okay? But even so, in general things, if you have a lot of clusters, it's good to have a hierarchy on top of it, okay? And sometimes you do have, and I think it's probably true that when you have a large number of clusters, perhaps the agglomerative clustering is a better way to think about it. Any questions? Okay.